So, yeah, it's all working. I'd like to welcome our next speaker, Michelle Hamilton from RAL Space. She is part of the Optical Sensors Calibration and Validation Group, but she's also our theme lead for Earth observation. Hopefully she'll explain it in more detail what that means, but basically it's essentially just like trying to develop RAL Space's strategy in how we collaborate within Earth observation. So I'll hand it over to her in a second to essentially just discuss all the different things that RAL Space is involved in terms of, you know, kind of how we can actually foster resilience within the space community as an organization. Thank you very much.
Okay, I'm holding this. Can you hear me okay? There's nods. Excellent. Right. Thank you very much for the introduction. So I'm from RAL Space and I will just move on. So first of all, I wanted to sort of give a little bit of an overview of RAL Space. We've already heard from Sarah, so some of this will all be very familiar. We've already heard it. But I just want to say our vision as RAL Space is that RAL Space is the UK's national space laboratory for advancing the understanding of space and our environment for the benefit of all. So that's quite grand, it's quite exciting, and there's a number of things that we're doing here. And so some of the statistics you've seen at the side here, Sarah has presented already. And what a couple of that I wanted to highlight were the fact that RAL Space has been around for over 60 years. So I've been involved in space missions for a long time. Been involved in over 200 space instruments. So they've got a lot of experience, and I just want to talk a little bit about that later. I'm going to talk about Earth observation. I'm a little bit biased. That's the theme leaders, but we do our other stuff as well. Oops, wrong button. Oh, no, we're fine. Good. So this is just a picture that I've taken, took that with a drone. That's some of the activities we do here at RAL Space. It's just a bit about the Harwell campus and RAL Space based on here. The most obvious building is the diamond donut we have here. Can you see? No, you cannot see that. Okay, so we also have the RAL Space building, and for the people who are in the room, you would have driven past that on the way in. And this is the building on the right-hand side with the yellow rim around it. And behind it, again, another big white building is the NSTF, which is the National Space Laboratory facility. Sorry, and this has got really large-scale instrumentation and chambers and stuff to work on full-size satellites. And then we move round. There's a building sort of over there. We have some people in RAL Space. And then some of us, they hide us right at the back of site. So up in the left there's a little white building you can see. We're not even that one, we're in the one behind that. So this is where we are on site. Now, why do we want to be here? One of the really exciting things about being here is that there are over 100, it's a gateway for space. There are about 170 space organisations, 100 representing at least 34 different countries based on this Harwell site, which is really cool for collaboration. So you're going from space agencies such as the UK Space Agency, then you've got NASA, ESA on site, you've got research institutes, you've got your large scale companies, your big primes such as Airbus and PAS, Lockheed. You have universities. Both those have been international universities or national universities. And then you get down to your small SMEs, so your medium, small enterprise companies have also got sites on here. So this makes it a really fertile community to be looking at space, and that's pretty exciting. So moving on to RAL Space itself, in a sense, RAL Space is structured around 3 science drivers. 2 of them here are resilient society and space science exploration. There are another couple of theme leads for them. I'm based around Earth observation, and I'll just talk a bit further later about some of the examples of the stuff that we are doing within Earth observation within RAL Space. So we have these science drivers, but they are underpinned by our data services, our research and technology, and our facilities. So this is the data, like supercomputers and computing services. And there we have the science and technology. So we are researching different sensors, different cameras, different mechanisms for making measurements and developing those technologies. And again, as I just alluded to as well, is the facilities we have here. So we have big vacuum chambers, so you can stick some in the NSTF, you can stick whole satellites inside those. But you also get much smaller chambers where you can stick parts of satellites and different instrumentation for testing to understand how they behave. We've also got facilities where we shake instruments around on big shakers, because obviously they've got to go through launching into space, and that's not that, it's quite bouncy. So you're able to check that all your electronics and everything will survive that process. So that is all underpinned here. And then again, all of this is enabled by engineering capability, the people that we have here, our relationships within the organisation, and this all leads to operational excellence over to deliver our vision, which I said before. So Earth observation is, I'm biased, I'm going to talk about Earth observation because I'm the theme lead for Earth observation. And this is what I really find exciting about Earth observation within RAL space is it does the full cycle. What I mean by that is we have researchers are thinking of the ideas and how could we make these measurements and the proof of concept and developing those ideas in someone's head into a bench top example of it, and then moving it through what we call TRLs, which are technology readiness levels. And these run from 0 through to 9. 0 being, I thought of an idea, to 9, you have got an instrument in the environment it's supposed to be operating, giving you measurements. And there is, you can step through those. So we do that here at RAL Space. And during that process, we also get involved in the mission concepts. How could you put this on a mission? What would you require? We get involved in the calibration and validation. So this is involved at all processes of it. If you're thinking about, if you make a measurement, a measurement is involved of a number plus some sort of an uncertainty. So you know how that measurement's made. And that's involved all through this process. So you don't get to the end and you have an instrument and you go, oh, better calibrate this. I don't know how, it's too difficult. But by thinking about that during the process and having that experience, you can make really robust instruments and measurements. There is one small step that we don't do here, which is launch. It's fine. We launched it up there, it's got into its orbit. And then we are also involved in mission support, getting the instrument ready to take measurements, making sure it's operating properly, taking those measurements. And then also once the measurements are down to the ground, we're into the storing of the data exploration and utilisation by the users of the community. And being involved in that, we understand the data, we understand if you're able to make this measurement, or if you can make this measurement better, we could do this sort of science. And therefore seeds the cycle again, going all the way around. So as an organisation and as observation, within RAL Space, we do that. And it's really exciting to be able to see that full cycle. So next, I'm going to talk about 3 or 4 examples of some of the research and some of the work that's being done within Earth observation. It's not everything, it's just some of the examples that I thought you might find interesting. So the first one of these is from the spectroscopy group. And this is the idea of taking an instrument from the idea of an instrument wanting to make a measurement through to a mission. So what we have here is an instrument that is looking at taking measurements of greenhouse gases. It's a lens sounding instrument. So it looks across the Earth atmosphere, and you can see the different concentrations of greenhouse gases, and you can do it with the different heights in the atmosphere. And this is an example in the lab. It's quite big. You can see that it takes up a bench top, and it's not only the instrument that's sitting on top of that table, it's also the electronics and the power supplies that are sitting under that table. So that's quite a large instrument. And through research and funding we've gone through here into moving into CubeSats, we've actually managed, well, the spectroscopy group and the engineers within our team have also managed to reduce this instrument down to the size of a shoebox, which is quite cool. And therefore, that also goes into a 12U, CubeSat. So, and that's also got your solar panels and your data downlinks and everything that you need also on your satellite. And this is part of what started off as a solstice mission. So the next example I have here is for calibration and validation. And there is a move in the space industry at present, what we're calling sort of new space, but there's a move from really big satellites to much smaller CubeSat satellites. And this has been driven by size. And as I have said before, it's really important that when you take measurements with a satellite, or you take any measurements anywhere, that you have some idea of the uncertainty. And this facility has been built to aid in working out the uncertainties you have on much smaller instruments. So we have big 3-meter chambers, 5-meter chambers here, which are a bit big if you're wanting to stick a part of a shoebox size instrument inside of it. So the small satellite calibration facility is moving to smaller instruments. So you have little cameras, so you're able to do this on a much smaller scale. And it has also been done in collaboration with NPL, which is the National Standards Laboratory. And so that means that all the measurements you're making are referenced back to SI units. And the calibration validation groups gets 2 goes this time. We're also looking at the development of different platforms, and this is some of the drone work we do within RAL space, and it's looking at what is called hyperspectral imaging. Now, hyperspectral imaging is a little bit different to your normal imaging. It is your normal screen, which you see here on your phones, are based on RGB. So you have a 2x2 matrix on the surface, which has had red, green, and blue pixels. And well, 4 of them, you have 2 green, we like green, and you have a red and a blue there as well. With hyperspectral imaging, and this particular technique of hyperspectral imaging, we have now replaced, the company have replaced the filters over the surface of this detector by a 4x4 matrix in the visible and a 5x5 matrix in the infrared. And this means that you're able to get much narrower information. So your green on your normal RGB camera, quite broad, fat wavelength range. When you run a hyperspectral, it's much, much narrower. You get much, much more information, get more spectral information. Why would we want to do this? Well, this means that we can, referring back to Eleanor's talk, we can do ground validation, looking at being able to validate what the satellite's seeing. We are also able to do finding out which wavelengths are really, really important and could be used for detecting, for this particular example, where you can see we're looking at a crop. Can we see crop disease? And are you able to detect that remotely? There's also looking at woodlands, and can you see tree disease? Are you able to look at and get speciation of different trees? Being able to map where things are and what condition they're in, and being able to do that on a satellite platform. There are obviously a number of other applications, but this group has focused mainly on the agriculture work. And the final example I have here is at the other end of the scale, and it's the remote sensing group. And this is where you're actually taking the satellite measurements. So we've got the satellite, we're now actually getting measurements from it and processing those so you can actually visualize them on the world. And this is taking from a number of different sources. I'm looking at Dora here. This is some of the work that she's involved in. And this means that it's not looking at long data, taking the long data sets and being able to visualize that on projection, but the group has also been able to do this on a near real time basis. So you can see this particular example, I believe, if you can zoom in, you've probably got a better option than I believe is CO2. So you're probably looking in this example of the CO2 from wildfires, and you can see how that CO2 goes around the globe in real time, and you can understand how your models are working. There is a little, and this is called Viz Tool. So I think if you can use the QR code up there, you can use that and have a look at these examples. And I will say thank you there. And is there any questions?
Is this working now? Thank you so much for the fantastic thought. I'm getting shout outs all the time. Needs to stop. Anyone in the room with any questions? Oh, we've got one. Nice.
You mentioned that you were using Earth observation to like detect, you know, how tree diseases and like crop yields and stuff. How does the resolution of the satellites, like, would it maybe be too low resolution to detect like long-term changes at the timescales?
So it depends what satellite you use. Some satellites you're looking at, say, a kilometre swath. huge, not that useful. But then some of your other more commercial satellites are looking at 30 meters, 10 meters. Now, when you're working into the hyperspectral, I'm using the numbers you can see in the visual are a lot smaller, but the hyperspectral, the satellites that are up there, the constellations that are up there, are tending to look at, I think 30 meters is pretty good. And if you're thinking of looking at crops, that is possible, particularly if you're looking at crops in, say, Australia, huge acres, great. But if you start moving to, say, somewhere more like Asia and that sort of thing, where you are dealing with mixed crops or much smaller sort of farm sizes, it does become a bit of a problem. But there has been work done on sort of mixels, which is mixed pixels, and being able to elucidate that information out. So you are looking at fingerprints and being able to understand how that would mix together. So it comes down to getting a lot of data and also being able to fly on these drone platforms to be able to make informed decisions about that and build your models.
Thank you.
Hi, I'm not sure if this is the appropriate time, but what are the different early careers opportunities that are offered in the groups that you have here?
Okay, so we do have, we're not the best person to ask. I know we have we do have the early careers scheme where they come through here. There is the opportunities to do collaborations with DPhils. There are graduates. There are other options to get into RAL space. I've got to stop there. I think there's people far better to ask.
I will make a note to add it to the end of my slides at the very end to mention, to do a bit of a shout out, so I'll discuss it later. But thank you, Michelle. Any more from the room? Yes, Tom.
Hi, Michelle. We had a quick question here earlier. You mentioned on standard cameras with RGB, there are 2 green pixels. Why is that?
Tom. I actually don't know, but I could guess that you're sitting at green as the middle of the spectrum. So that's where you want to be most sensitive, is where the most light comes in. So I suspect that is why. Yeah, I'm going to.
Any online, Anna? Is there anyone at all online? That's good to hear. Good to hear. We'll take one more in the room. Perfect.
I think you were looking at using a lot of like small satellite missions. Have you thought about looking forward into the future, as I know there's a lot of space trash in low Earth orbit, and how this will all work in the future if you can't just keep sending up small satellites to take all the data measurements?
Sustainability in space is a very real concern. A lot of CubeSats are set on a descending mission orbit. So they will be up there for a period of time, and then they'll come back into the Earth atmosphere and burn up. So that is one way that we are not necessarily putting more up there. There is a lot of, we're putting more up there, but it's coming back down. There is work done by other companies, not necessarily RAL Space, about sort of grabbing space debris and being able to collect it up and bring it back down. It is definitely a very real concern. Some of the work that's been done at Chilbolton, which is the other site, RAL Space has 2 sites, main one here, and there's a clean air site at Chilbolton with a 25-metre radar dish. And they do tracking of space debris as well, and sometimes not space debris, actually satellites, but that is one of the things that they're involved in as well.
Thank you very much. I think we're probably right